Let's see.
I'm just gonna make noise all class. Put that there.
Okay.
Sheet of a sheet of some sort for our dynamic spinal.
I can try to look into the formula sheet.
Oh yeah, speaking of, formula sheet for this class. Make sure it's sent to me before Monday. I want to see it before Monday. Alright.
You want a lot from this.
Mm-hmm. Well, you don't have to submit a formula sheet if you don't want to, but then you're on your own. Otherwise, if you guys just want, I'll just give you guys the formula sheet from exam 1. Which, that was just, let me see,
Questions?
4.
So
Plus the
one
bonus.
from 9, one from 10, one from 3, and one from 11.
Yeah, 1 from each chapter, basically. Yeah. If you guys don't send me a formula sheet, this is what I'm giving you guys. This whole thing. Because this was what it was for me when I took the class. And I was only allowed to use this. Alright, so you can either take advantage of the fact that I'm giving you guys the ability to create your own and put whatever you want on it. Or you guys just tell me you want to use this, and it's fine. What do you guys want to do?
I see no chapter 11 on there, so we gotta pick our own.
Mm-hmm. Yeah, because when I took the class, chapter 11 did not make it. They were too far behind. And I don't think he even does chapter 11. I like doing chapter 11 because it's fun. All right. So today we're doing review. If you guys have any particular sections or problems that you guys wanted to work on, let me know. But I just chose basically a few problems, each from one of the chapters that we could just work on collaboratively. For this first problem, all I am asking you guys to do is to determine the reaction at the roller supports. All right, let me just pull out my appendix, which this is your guys' exam that I already created, and on all of the exams you guys have reference sheets. Nope. No. Okay. Here's the next page. It's blank. All right. It's literally the same thing as what's here. All right. Yeah. And the only reason for that is because you guys can, like, if it's a superposition problem that you guys feel like you could solve using superposition. I was able to do it using that appendix, so everyone should be able to as well. You don't have to do it that way, just as long as you get the answer right. But anyways, this problem we're asked to solve for the roller support. So I first want to ask, how do you guys think we do this? What would you guys do? Let me just insert a few blank pages. You want to do equilibrium first? How do we solve statically indeterminate structures? There's a few ways we can really solve this. Some of the redundant.
No, remove the.
Remove the redundant. I thought you said. Did you say some of the redundant?
I might have slurred my own.
All right. So remove the redundant and then replace it by its equivalent reaction force. So this problem here, we can separate into two systems. One with a moment, and then what's the other system gonna look like?
Just gonna have a reaction force going on.
Yeah, so this is just gonna be RB. All right, so what do we do from here? What do you guys want to do? Yeah.
Can you technically do principle of virtual work on the moment cantilever to see like the vertical
You can do principle of virtual displacements or virtual forces, or however. Now, if you wanted to do principle of virtual forces, you would still, yeah. I guess we could do that, which would require you to know the bending moment diagrams, right? So, yeah. But, well, we still need to solve for the initial system, right? So we still need to solve for that very left-hand system. How does the bending moment diagram look for that?
It's just constant throughout.
Exactly. Positive or negative bending? What's our reference fiber? The design one.
Take it from the bottom.
From the bottom? All right, so we'll say that the reference fiber is the bottom. Now, if we tried to do equilibrium, we'd find that the reaction moment here is just m naught, which then means that our internal moment is this, m naught. Now, when we cut sections, recall, let's say that this is the cut. This was positive m of x, right? When our reference fiber was on the bottom. So what does that tell us about our internal moment?
It's going to be negative.
It's negative. So we get negative m naught. All right. So the next step would then be to do the principal virtual forces. Is that what you want to do? We could do double integration method. Like, I mean, on a problem, unless I specify a very specific thing, which I will tell you guys, I don't generally do that. I didn't do that for the statically indeterminate problem I put on your exam. You guys can use whatever deflection method you want. There are a few questions where I did specify use a particular method, but for statically indeterminate, no. So you want to use principle of virtual forces? You guys want to do double integration? What are you guys thinking?
Virtual.
All right, good. So we know from here, let's make an assumption about which direction the force is going to go. Upwards, downwards, where do you think the deflection is going to go? Let's take a guess.
Downwards.
Downwards? All right. And we set this equal to p bar is equal to 1, right? Now, similarly, this is going to result in negative bending, but the bending moment diagram, because it's a point load that's applied, is going to be linear like that. Now, both of these are length L. They're both negative. So this is just going to end up being negative L for the bending moment, or negative 1 times L. All right, but what we need is technically this m of x. What is m of x? X goes this way. Well, I think that m of x would just be equal to x minus L in that case. For x equals 0, you get that m of x is negative L. For x equals L, you get that the bending moment is 0. So it aligns. From here, we're going to solve using principle of virtual forces. And so we calculate the strain energy equaling 1/2 times the integral of, this is m of x, and this is technically m bar of x. So what we have is m of x, which was equal to negative m naught, And then we have m bar of x, which is equal to x minus L. EI is assumed constant unless we specified it in the problem, which we didn't in this case. So we could just safely assume EI is constant throughout. From here, we just set our bounds of integration from 0 to L, since that is the range in which those diagrams are. So we get 1/2 times the integral. Technically, we could carry out the m naught. So this is negative m naught divided by 2ei times the integral of x minus L dx from 0 to L. Continuing with the integration, we get x squared divided by 2 minus Lx from 0 to L. And then this is just going to equal negative m naught divided by 2ei times L squared over 2 minus L squared, which just gives us m naught L squared divided by 4 EI. Now, for the virtual work for the problem, W bar, we set this equal to 1/2 times P bar times delta, which is our deflection, which we're going to say is Y. But P bar is equal to 1. So this just becomes 1, which means that our vertical deflection at the free end is equal to m naught L squared divided by 2 EI. Where do we go from here?
I can go back to just the reaction force.
Exactly. So back to the reaction force. Let's go back to the reaction force now. So I'm going to copy this and just paste it in here. And now we have our reaction force, which our reaction force RB is going to result in this being a positive bending moment. Which I get RB times x minus L. Now, we can do principle of virtual forces again in order to solve that, where now we would have U bar for the principle of virtual forces equaling 1/2 times EI over the integral of 0 to L of RB times x minus L multiplied by x minus L for this bar dx. Now we can technically change the assumption about P bar, right? In this case, we don't need to. The math will just show us the direction. So we're assuming that from this case, due to the vertical reaction upwards from RB, that it's deflecting downwards. So for our answer, we should technically get a negative value for the deflection. All right? Does that make sense, what I'm trying to get at? Because P bar is about our assumption that we're making. If you wanted to change it to where P bar is equal to 1 going upwards, then the value would just end up being positive. Does that make sense? And technically, this should be, I think, just for consistency, I want to set RB is equal to that. Because I think then at that case, it's consistent. Yeah. Yeah, because then technically it would have been RB times L minus X. All right. So from this, 1 RB divided by 2 EI times the integral from 0 to L of x minus L squared dx. If we expand this out, I just want to do x squared minus 2xl plus L squared dx. RB divided by 2EI times x cubed over 3 minus x squared L over 1 plus L squared x from 0 to L. Let me grab a calculator. And this should give us 3 minus... Yeah. This will give us a strain energy equaling RB L cubed over 6 EI. Which means that when we set W bar is equal to 1/2 P bar times Y, and we set P bar equaling 1, we should get that Y max is equal to RB L cubed over 3 EI. All right. And those are just the deflections from those two systems. Now, on an exam, again, I give you guys these nice little tables. You just wasted about 15 minutes if the deflections are on here. All right, which I will tell you they are, but it's good practice for this case. All right, so I can tell you that for a point load, the deflection is PL cubed divided by 3EI. And then for a moment, the moment deflection is ML squared over 2EI, which is what we had previously computed here. So the values are correct, which means our assumptions for calculating the deflections currently are correct. All right, but that doesn't exactly solve the problem yet. Now we just only found the deflection, so now let's apply compatibility. So through compatibility, we know that Y of our initial system, the zero system, that's going to be the one with the the M naught applied to it. And then we're going to have the Y of the one system, which is going to be the deflection of the reaction force. And the sum of those has to equal 0. Now, from this, we know that the deflection for this was m naught L squared over 2EI. Because of our assumption for P bar, we assumed that it was going downwards, right? So when we ended up with this value, it ended up being as is. Now for this, we got RB times x minus L and then x minus L. I believe this should technically be negative because this would show us that the deflection should be going upwards because technically RB should be really going upwards. No, because RB we assumed going downwards. This is the thing that kind of gets confusing at times. So RB we're assuming going downwards, which means our deflection should be showing positive, and we're making an assumption that RB is still going downwards in this case. I know it's a little weird, but it's an assumption embedded into another assumption, so it can get a little confusing if you're not careful. Does that make sense? Because we're making an assumption about the direction of RB, and then on top of that, we're making an assumption about which direction RB is going or causing deformation. So that assumption is embedded into an assumption, which is where things get a little tricky. But basically, we're both assuming that Y max for both systems are going downwards. So what we end up with is m naught L squared divided by 2EI, and because it's downwards, we write negative, plus negative RB L cubed divided by 3EI is equal to 0. The EI's will cancel. The L cubed gets reduced because of the L squared. And what we end up with is RB is equal to negative 3 over 2 M naught times L. Nope, M naught divided by L. You can't have M naught times L. All right, now what does that mean about RB being negative? Which assumption did we use for RB? We assumed RB was going downwards, right? But because we got a negative value, that tells us RB is actually going upwards. So this negative value means that RB is equal to 3M naught divided by 2L going upwards, and that is the reaction. Any questions about this? No? All right. Now, I've got another example here. A W14 by 82 column of 50 KSI steel supports and a factored load of 776 kips. So that's your design force. So a factored load is just another way of saying a load with some factor of safety included in it. The column is sufficiently braced so that minor axis buckling does not govern. A W14 by 82 column has a cross-sectional area of 24 inches squared and a radius of gyration of 6.05 inches. Most nearly, what is the longest effective length that the column can be designed for to prevent buckling? Fun fact, I took this from one of my PE review courses. It's no more than probably like 2 minutes though. I want to see if you guys can't figure it out. Just take a minute, maybe try and draw out the problem and see how you would solve it. In the meantime, I'm just going to get a quick refresher of the solution. I just got to dig deep into my PE notes. Let's see. Where is it? It's in here somewhere. Here it is.
this is kind of an AST solution, but the answer will slightly be updated based off of. Ignore all of these options, by the way, because
I just did it using the assumptions in our class. I took this from from the steel section, so it's going to include some code-based stuff. But I was able to do it using elastic methods just now. So it's not going to be any of those answers. Who here's got it? Come on, I was able to figure it out just now.
I got an answer.
What'd you got?
I don't know if it's right, I got 22.6 inches.
22.6 inches?
23.6 inches, but
What type of column is 23.6 inches?
I don't know, that's why I don't think it's right.
What was your approach?
So the radius of gyration squared is equal to I over A. I solve for I, and then using I, E, and then the pressure, the load that you're given for the PCR is equal to pi squared EI over L effective squared.
Mm-hmm.
I tried solving for L effective.
Well, here's the nice thing. The radius of gyration in the major axis is 6.05.
Yeah.
So you don't even need to solve for I. Because,
Is there like a separate formula?
well, it's what you said. The radius of gyration squared is equal to the second moment area of inertia divided by the area, right?
Yes.
So Ix would technically just be the square root, the radius of gyration squared times the area.
Yeah.
Yeah, is that what you...
That's what I did to solve for I.
Yeah, but how did you... But still, that seems very low, the K. Let me see. I want to see.
I don't know if I switched that in the wrong place, so area was 24, radius was that I ended up getting,
So you did 6.05 squared times
yeah,
24.
5 squared times 24, that got me 878.46.
That's your issue. What's the equation for critical buckling?
Isn't it?
E. You're
Yeah.
using sigma.
Oh,
Yeah. What's the elastic modulus for steam? Should be 29,000.
that checks out.
Now try it. Divided by 12 now? That's the answer.
Okay.
All right. Cool. One student got it, which means everyone should have gotten it. All right. Raise your hand if you got it. You did. What did you get?
47.4 feet.
Yes. What did you get?
47.
47.4 feet. What did you get? No? Carlos, how about you? Did you get it? No? All right. Let's go over it. All right. So, few ways you could have done it. You could have just calculated I using the radius squared times the area. The way I did it is I used the equation sigma is equal to pi squared E divided by lambda squared, where lambda is the slenderness ratio. That was the LE divided by R. And so what I did was I first just rewrote this to then just be that the slenderness ratio is equal to pi squared E divided by sigma. Now, sigma is also equal to P over A, so it's 776 divided by 24, which gave us a stress of around 32.3 KSI. All right. Now, that's a good sign because our stress is still within the 50 KSI, which means that the column at least works. All right. From here, I figured out what the slenderness ratio was by just plugging in pi squared. The elastic modulus is 29,000 KSI, and then the stress is 32.3 KSI, which gives us a slenderness ratio of 94.13. From here, we know that the slenderness ratio is defined as KL over R, which KL is just the effective length, LE. So LE is just equal to lambda times R. In this case, because R is in terms of X, we're going to have lambda X. So all of these are with respect to major axis bending. So this is just going to equal the 94.13 times the 6.05 inches, which will end up giving us 569.5 inches, which then divided by 12 gives you approximately 47.5 feet. Does that make sense? Again, the other way you could have done it is by calculating I using r squared a. That just comes from r is equal to square root of I over a, or r squared is equal to I over a. And then from there, setting the 776 equal to pi squared EI over KL squared, rewriting it just to solve for KL, and you would have gotten the same answer. Make sense? All right. Small question, but it can get a little tricky, especially if you don't see the problem, and you might question well, what's the K factor on the column? Keep in mind, the question asks for the effective length. What is the effective length? That's the length with the K factor included. If you wanted the total length, then you would need to know what the boundary conditions of the problem are in order to be able to find the total length. Make sense? All right. Now, here's another question. A one-story steel moment frame is subjected to gravity loading. The frame is 20 feet high and 30 feet wide. The frame is not braced against side sway, and the columns are flexurally fixed to the beam, meaning that EI of the beam is significantly larger than EI of the columns. Assume the frame is braced out of plane. Given that the product of E and I, which is also termed flexural rigidity, is 2.8 times 10 to the 6 kips. It should not be kips per square inch. The units of this should be kip inches squared, so it's kips times inches. Determine the critical buckling force for each column. It's kip inches squared because the units of the elastic modulus are kips per square inch, and then I is inches to the fourth. So it just happens to be kip inches squared is the term. All right, so take a few minutes to try and solve it, and then I want to see what you guys end up with.
Is there gonna be a frame problem on
This is not even a frame problem.
the like?
Think about, it's actually a column buckling problem. And no, there's no frames on the exam, because frames are a little too complicated. I did put a frame problem on the optional homework 11, if you guys happen to take a look at that. But no, you guys won't see a frame problem on the exam because there's not enough time for you guys to be able to solve it. If it's a column buckling problem, I could give you guys a frame like this, but it would be isolated to only a specific column, in which case then you may need to know the boundary conditions and how the column would behave due to the adjacent structures. For example, it might be calculating the G values and then using that table to determine the K factor. Or it could be something like this where I specified the beam is infinitely stiff. And so you have to make an assumption about that. Will, you raised your hand back there? Or?
I found the answer. I couldn't see that was a 6 or an 8.
Oh, okay. Yeah. Now, I will give you guys a hint. You guys will need to know the K factor for this problem. So I would highly encourage you guys to look back at the notes or the lecture slides in order to figure out the K factor for it. And think about how the structure would deform. How would it buckle? I know I'm having you guys do a lot of thinking today. I'm sorry. And if it makes you guys feel any better, I showed Wesley your exam. He said I'm going a little too easy on you guys. But that's coming from Wesley. I don't know. That would have sucked if that broke, but I'm assuming you welded it good. It's steel for crying out loud. I don't know what that is. It's not the fire alarm. That would be going off. Who here's got it? Still no one? Travis, tell me you got it. No?
I don't know what I said. I was thinking of it one way, but don't you guys need
fixed, but side sway isn't negative.
Yeah,
Or, I mean, negative 10.
yeah.
So. I will tell you, the EI for the beam is significantly larger,
Yes,
and it's treated as basically a fixed end.
yeah.
But, here's the thing. Is it braced against side sway?
It's not.
Right, so draw how the structure would deform. You guys have
What chapters was exam 2 on?
What?
What chapters was exam 2 on? It was
4, 5, and 6 was chapter exam 2.
yes.
How?
Yeah.
How?
Held?
Mm-hmm.
What's wrong?
No, it just.
Alright, you guys just wanna do it? Alright. So, alright, so for this problem, it's as simple as just using PCR is equal to pi squared EI over KL squared. What? You're right. Alright, now, PCR is just equal to pi squared times 2.8 times 10 to the 6 kip inches squared divided by, basically it's going to be k squared times 20 feet times 12 inches per foot squared. So PCR is equal to pi squared, or, well, yada, yada, yada. So you get pi squared times 2.8 times 10 to the power of 6 divided by 20 times 12 squared, which gives us 479.77 divided by k squared. So then the question is really, what is the k value that we need to use? All right, so how would the structure deform? It's gonna be able to laterally move, right? So if we draw out the deformed shape, it's gonna be fixed, which means that under some type of buckling, it can deform like this. All right. Now, one of the nice things about this is the fact that it's actually a standardized K factor. I noticed once I walked over to one of yous, I forget who, but I was looking through the notes. I don't think the K factor is shown, but let me just show you guys what I mean. So, column buckling K factors. Ideally, you would have been able to use the G table. I just saw, like, some of you weren't making the right assumptions, but ultimately, what we need to look at is this. All right, so a table like this covers all the K factors. I think the table has it also. Don't pay attention to the recommended design value. That would be something that you would see for like advanced courses that are code-based design values. What we're ultimately looking at for elastic method is just the theoretical K value, which is what you would get from derivation. So in this case, the K factor for this type of column would be about 1.0. All right. If we go over to this column here, actually no, this one is 1.2. No, it's 1.0. That's the theoretical recommended. So the K factor for this type of column is 1.0. Even though it's not pinned, if you were to think about how it deforms and continue its curve, the effective length is identical to that of the pinned connection. So what we have is basically K is just equal to 1 in this case, which means that your answer is D. Now, if you were looking at a more advanced topic and actually dealing with the recommended design value from like a code-based perspective, that design value becomes 1.2. I know it's a little hard to see from this figure here. You can kind of see it right here, the 1.2 for an unbraced column. In which case then that answer would just immediately become 330. But because we're only dealing with elastic analyses and making assumptions that are entirely purely based off of determinable values, then the answer would just become D, 480 kips. Yeah.
If we didn't know like the standardized K value, something like that, would you?
I would give it, or it would be something that you could definitely figure out from the alignment chart.
Okay.
I just didn't feel like using the alignment chart. But like, I mean, if I don't specify a K factor, it's either I'll give it to you in a table that you can use. You'll either, or you guys get the alignment chart, or if it's just pinned and pinned, K equals 1. All right, that's the easiest way. All right, does that make sense? Are there any questions about this problem? No? All right. Now we have this problem. An ideal truss has nodes at the indicated coordinates. The truss is supported in the X and Y directions at A and in the Y direction at D, as shown. At B, a point load of 3 kips is applied in the negative Y direction and a point load of 5 kips is applied in the positive X direction. The product of area and modulus of elasticity AE is 1,000 kips for each member. The internal loads in members AB, BD, AC, and CD are 2.67, negative 5.50, 2.92, and 2.92 kips, respectively. All right, so it gives you the internal forces of the members already. The length of members AB and BD are 12.81 feet and 9.43 feet, respectively. Most nearly, how much does node B deflect in the X direction? I'll give you guys a few minutes to figure this out. Are you not happy with the question, Andres? He's shaking his head at me. I think he's upset.
The final is 9, 10, 11.
9, 10, 3, and 11, yes.
Okay.
Mm-hmm. It's not too bad. Just only 4 chapters. And they're the easiest chapters of the semester.
No, 100 pages.
No, I was able to do all of the calculations within an hour and 15 minutes, and then able to do everything all on one page. And that was with me making revisions to the solutions to try and simplify it a bit. So what's the thought process? What are we all doing?
Principal virtual course.
Okay.
It's just a lot of numbers you have to solve for.
Are you, you're not solving for the internal forces with that loading, right?
What's up?
You're not solving for the internal forces with the 3 and 5 kip loads.
No.
Okay.
Yeah, I'm solving for the virtual.
Okay, yeah, just the virtual you
Yeah.
only need to do.
Yeah.
Just making sure you guys didn't miss over the fact that I gave you guys the internal real forces already. Figured out? No? Shame. What?
I will on test day.
You will on test day? Alright. Do you guys want to go over it? Alright. So, is my screen frozen still? Yes, it is. Alright, so I drew out a figure. Alright. So the idea is we want to apply a virtual force at the location we're interested in. So as in the problem, it asks us most nearly how much does node B deflect in the x direction? Right here. So that tells us we want to determine the lateral deflection at point B, which means we apply a virtual force P bar equal to 1 at node B going in the x direction. We're going to assume that it's going to the right, so that's okay. So from here, we solve for internal equilibrium, external equilibrium. We'll find that HA, I'm going to label that HA bar, VA bar, and VD bar. So HA bar we know is going to equal 1. From here, we do sum of the forces, or sum of the moments I want to do, about, let's say, point A. And we get P bar time, which is 1, times 8 feet. And this is going counterclockwise or clockwise, plus VD bar times 15, which means that VD bar is just going to equal 8 over 15. This means that VA bar is just equal to 7 over 15. Wait, no, negative 8 over 15. From here, we look at method of joints, or method of sections, preferably method of joints. All right, right off the bat, BC is a zero force member, just from this loading. Let's look at joint D. So I want to do the force body diagram at D, because that seems easy enough. We know that the vertical force at D is going to be 8 over 15. And then we are going to have CD going to the left. We're going to have BDX going to the left and BDY going up. We know from some of the forces in the y direction that BDY is equal to negative 8 over 15. And then just from geometry, we can kind of use law of sines or just the geometry of the problem to then basically relate BDY to BDX, where BDY divided by 8 feet is equal to BDX over 5 feet, which means that BDX is equal to 5 over 8 BDY. Which gives us, 8 over 15, 1 over 3. All right, now I'm going to redraw these arrows here to then just be going downward. So I'll do those in like this dashed line here. From here, we could do sum of the forces in the x direction, and we know that this has to equal 0, and we get negative CD plus BDX, which is 1 over 3, which means that CD is equal to 1 over 3. And CD is obviously going to be in tension. All right, we can solve for BD by taking sum of the squares. So we've got 8 over 15 squared plus 1 over 3 squared. Which gives us root 89 over 15, which because of the negative sign for BDY and technically BDX, we know that the member has to be in compression. Make sense? All right. So from here, because we know that BC is equal to 0, we know that CD is 1 over 3 in tension. From forces at C equals 0 in the x direction, we know that AC has to be 1 over 3 in tension, and then we computed BD is root 89 over 15 in compression.
Last step, let's just do force body diagram at A. We're gonna have HA bar going to the left. VA bar is going vertically downwards at a magnitude of 8/15. And then we've got AC, which is equal to 1/3. And then we're gonna have ABY and ABX. From sum of the forces in the X direction equals 0, we have -1 plus 1/3 plus ABX. And this gives us ABX is equal to 2/3. And that is obviously going to be in tension. From forces in the Y direction equals 0, we have -8/15 plus ABY, which means ABY is equal to 8/15, also in tension. All right, now quick sanity check. From sum of the forces in the Y direction at B, it means that the Y component of AB has to equal the Y component of BD, right? So BDY was equal to -8/15, and ABY is +8/15, so it makes sense. So that gives us AB is just equal to the square root of the sum of the squares, so it's 2/3 squared plus 8/15 squared. Which gives us 2√41/15 in tension. From here, we develop a nice little table. We were going to have a member table. We're going to have an N table, an N bar table, and then we calculate N bar L over EA for each member. So we are going to have AB, BC, CD. Then we've got BD and AC. In all instances, BC is 0, so that's 0, 0, 0. Remember, AB was specified as positive 2.67 kips. AB for this one was 2√41/15. For CD, or BD, I'll say, is -5.50 in compression. But BD was calculated as √89/15 in compression, which, because it was in compression, throw a negative sign there. For CD, we got 1/3 in tension. I'm going to throw positive signs here. CD was 2.92 kips in tension. And then it was 2.92 for member AC also. And that force was 1/3. All right. Now really quickly before I do this, whoops. I want to get the L's basically written out for all of our members because the L really varies. So the length of each member, AC was 10 feet. The length of member CD was 5 feet. The length of member BC was 8 feet, not that it matters. The length of member AB was specified as 12.81. And then the length of member CBD is 9.43. Now, EA was specified as 1,000 kips. So that means that when we plug everything in, for example, 2.67 times 2 root 41 over 15 times 12.81 divided by 1,000. Member AB becomes 0.0292. And then you just repeat the process for everything. 2.92 times 1 over 3 times 5 divided by 1,000. This gives us 73 over 1,500, which I'm just going to keep everything in decimal just to make things easier. 0.0048 or 49, I'll say, just round up. Negative 5.50 times negative square root 89 over 15 times 9.43 divided by 1,000. This is 0.0326. And then 2.92 times 1 over 3 times 10 divided by 1,000 is equal to 0.0097. And you take the sum of all of that, and that is your total strain energy. 0.0292, 0.0049, plus 0.0326, plus 0.0097, which gives us a total strain energy of 0.0764. Last step, what we do is we set U bar is equal to W bar, which is just going to equal 1/2 P bar, which is 1, times delta, which is the deflection. And that was equal to the 0.0764, which means that our deflection is just 2 times that. So it's 0.0764 times 2. 0.1528 inches. And that is the, feet. Because our L was in feet. Which, when you multiply this by 12, gives us 1.8336 inches. Everyone understands why the units are in feet, right? Because the lengths that we input were in feet. All right. I have one more example problem, but it's past the time, so if you want to leave, you can. Otherwise, we'll work on this one last problem, and then that'll be it. So I'll just give it a few seconds to see who leaves, who stays. But in the meantime, I guess everybody who wants to stay, feel free to try out the problem in the meantime. I'll increase the size.
Thank you, have a good night.
You as well. You too.
Have a good night.
You as well.
See you next week.
Yep. See you next week.
Compatibility,
Not statically indeterminate.
not statically determined. So you're not setting, this is not like the homework.
Yeah.
right?
Um,
Like, I can't set both sides of the equation equal to, like, both equations equal to each other.
it's not statically indeterminate. You don't need to do that.
Oh, okay.
And matter of fact, I don't know why it says 46 millimeters here. I think that's just an error, unless that's just the answer, but I don't know. So that's some diameter D.
Oh, also, by the way, the link to that survey has been closed. We can't do the survey.
You can't do it? Why was it closed?
I don't know.
Was it just expired?
I guess. I don't know, maybe. I tried maybe the other day and they said that the data collection has, like,
I'll follow up with them to see if they can. Otherwise, what I'll probably do, because I have technically results from last semester, which one student did it and he was a hater. I'll probably copy paste all of the questions from that and create my own and send it to everyone. And then I'll make it so that way everyone has to input their emails, but I'll try and make it to where the responses are anonymous. Yeah, because again, I want you guys to be open and free about it.
Also, after we solve this problem, can you go back to the first one and do it differently?
Sure.
Because I know we just learned the
Strain energy, but you want to just try a different method with the deflection? Okay.
Just in case, like, the problem shows and then I feel more comfortable doing the deflection.
Mm-hmm.
Like, if the problem.
Yeah. Well, technically, the first problem we did was kind of like doing it two different ways, because technically, like, we did strain energy to obtain the deflections, which, you know, you can fact check using those standardized tables. So if you wanted to just use the standardized tables that I provide you on the exam, you can do that, in which case those values will just, you know, it's just a matter of applying compatibility at that point and it kind of avoids having to do all of those first steps. But the only other way that you can really do it is by using the double integration method and then applying the boundary conditions to determine the unknown constants. You want to do it that way?
Like, what would you say that way would take much longer?
It would. It would take a lot longer.
But, okay, so if I can ask, with regards to what is on the test, will I be given, like, I'm afraid to rely on what we just, using that and then coming across the test and then I'm gonna be like, oh shoot, I should have.
So I do put one principle of virtual work or strain energy problem on the exam. I put one deflection problem on the exam, which is technically the statically indeterminate problem. But I give you guys pretty much freedom to solve for the statically indeterminate problem. You know, because at the end of the day, you gotta figure out the deflection anyways, and you can use any tool you want with that. So unless I specifically specify the method that you have to use to solve it,
You can use either one.
yeah. If I specify a method that you have to use, it's gonna be for statically determinate. Statically indeterminate, do whatever makes you feel comfortable. It's just a matter of knowing the principles on how to solve the statically indeterminate problem. Make sense?
So then it's fine.
Yeah. But do you still want to do the double integration or? Okay. Yeah.
I have a question about the bridge.
Sure.
I might make an RFI about it, but for the abutments, are they gonna be the same as how the plans are, where it's like 2 huge pillars, or is it just gonna be like a flat table?
It's probably going to be a flat table.
Okay.
I don't have the capabilities to put 2 giant pillars on it. Yeah, so it's probably just going to be 2 tables and it's just spanning. I'm going to make the dimensions, like make it so that way the area that those quote unquote pillars would be the area where those quote-unquote pillars would have been. Because if you ever watch any of the videos from the ASE competition, they actually have like circular pedestals that they rest on. In this case, we don't have that. So that 2-inch, I think it's 2 inches of width, that'll be measured along with the span length. So I'll make sure everything is very similar, if not identical, to how it's shown on the plans.
Okay, that makes sense. Then as far as like the front face of it, it's just gonna be like this and a normal table, or the table thickness only.
Say that again?
Like, as far as like the front face of it, you know how the abutments like were flush all the way down?
Mhm.
I imagine just gonna be the table thickness only, right, going down?
Yeah.
Makes sense.
Yeah.
Just wanted to make sure.
Basically, don't hit the table, is the idea, you know?
Okay, cool. Alright, cool. Just wanted to be sure about that.
Now, as for what table, not fully sure yet. I believe we're gonna try and get into that room during the loading day because there's not gonna be anything going on, especially since we can't use these desks.
Yeah.
Yeah,
Nah.
they'll tip over, so you need something that'll have like extra weight to kind of support it. So we're either gonna be doing the room that's across over there, or I'd preferably like to do Simon's room, which is way down at the end of the hall over there, across from the men's restrooms. I'd like to especially do those because the tables are thicker, and the tables are already beat up. So I don't want to like destroy anything.
Okay, that's great.
Yeah, because remember, we're loading 70 pounds. Well, actually, it's only going to be about 35 pounds per table, so that's fine. Because it's
They distribute.
give or take, yeah, depending on which point I decide to load it from.
Are you testing all points?
I can.
But like, do you think we'll get through it with when you're gonna test all points, or like you're just gonna choose a random one and be like, okay, this is-
I'm thinking of just choosing a random point, but
Well, obviously you have to design so that all of them.
yeah, so you design for basically the envelope of all worst case scenarios. Yeah.
I like Simon's room better anyways. It's kind of cooler in there. Have a good day, Professor.
You as well. Say that again?
Like, go over it.
You want to go over it? All right, we'll do it real quick. All right, so what we need to recall is the, this problem doesn't, I chose this problem without giving you any fucking parameters. That would be one of the problems. Yeah, you need a maximum shear stress. So let's say that's, I don't know. What's a good example?
Is this from the textbook? Do you want me to go check and see if it's given?
No, we could just assume something, because then the maximum shear stress would just change accordingly. So if it's type A992 steel, it's just going to be roughly 60% of that. So that's about tau max equaling 30 KSI. Let's say I want to use a factor of safety of 2, which means that the allowable stress is 15 KSI. All right, so that's what I want to use for this case. All right. So from here, they're all in Newton meters. Crud. Let me, good thing I have this, because this will tell me the maximum shear stresses of the different materials. For this, I don't know. Yeah, let's pick steel. A992 steel, which was 77.2, no, it's, tau max is equal to 145 MPa. Use a factor of safety of 2. So then I'll say tau allow is equal to 72.5 MPa, which is the same as just saying newtons per millimeters squared. All right, from here, we know that tau allow is equal to TR over J, which then we can rewrite as just saying T times the diameter divided by 2 divided by pi over 32 times d to the 4th. What we need to do from this point is just rewrite this to get d by itself. So this would just equal 16t divided by pi d cubed, I believe. Right, because pi over 32, the 32 gets carried to the top, then divided by 2, the pi remains on the denominator, and then the d cancels out from the top going to the bottom. All right, so then we rewrite this to be d is equal to the cube root of 16t divided by pi times tau allow. And it should be cube root. All right. Now we want to keep consistent units. So the torque, the total torque within rod DC is going to be the reaction torque here. So TC is just going to equal 700 Newton meters from equilibrium, which 700 times 1,000 is 700,000 Newton millimeters. From here, just plug and chug. 16 times 700,000 divided by pi times 72.5. And this gives us a diameter of around 36.6 millimeters. And that would be the answer. Now, if I asked you guys, design it so that the rotation is limited to, let's say, 1 degree. All right, so we'll say that phi max is equal to 1 degree. All right, so we're applying now a serviceability criteria to it. And this is going to be the rotation at, let's say, joint point A. So this is the max rotation at A. What this is going to equal is basically the sum of all of the TL over GJs for each. All right. So 1 degree is equal to pi over 180 rad, which is equal to the torque in BC, which is 700 Newton millimeters. Well, technically, yeah. Times, 700,000 Newton millimeters. The length of rod BC would just be whatever it is. I don't know. Let's assign some random values. Let's say that this is like 100 millimeters, and this is 100 millimeters also. All right, so 100 millimeters divided by G, which you would need to be given that, so it would be 77,200 newtons per millimeter squared. That's the same as 77.2 gigapascals, which would be given to you on an exam if you couldn't get it from a table like this. And then J is just pi over 32 d to the 4th. And that would be for rod BC. And then we add rod AB to it, which then the torque in rod AB would just be the 700,000 minus the 400 Newton meters, which gives us 300,000 Newton millimeters. The length of that rod I just said was 100 millimeters. We're assuming the same material, 77,200 Newton millimeters squared. And then the diameter was 30 millimeters. All right, so we get pi over 180 radians is equal to 700,000 times 100 divided by 77,200 times, all right. Then multiply that by 32 divided by pi. This is roughly going to be 9235.93 d to the fourth plus 300,000 times 100 divided by 77200 times pi over 32 times 30 to the power 4, which is 4.89 times 10 to the negative 3. For 180 minus that answer gives us that. And then 9235.93 divided by said answer is that. And then you take the square root of the square root of that answer, which gives us D is equal to 29.28 millimeters. So in that case, the 36.6 millimeters wouldn't work. Make sense? So in a case where whenever a deformation criteria is specified, you want to check the deformation. And then you would pick basically, actually no, wait, the 36.6 would work. All right, I had that backwards, right? Because we realized that the minimum D needed to be 36.6 in order to make sure it worked. So this is smaller, which means the stress would be exceeded. So I retract what I said about that being the answer. The total answer, if a deformation criteria was specified, would be this. Any questions about this? No? All right. Your projects are due at midnight. Everyone feeling happy that this class is almost over? No?
It has to be in reverse.
Mm-hmm. All right.